So good morning or afternoon, wherever you may be in the world. I am Dr. Diane Gardner. I am the leader of the Resilient Structures and Construction Materials Group in the School of Engineering at Cardiff University in Wales in the UK. And today I'm going to be talking to you about the development of vascular networks for self-healing concrete. First of all, I want to really sort of introduce perhaps why we need self-healing concrete. What are going to be the advantages of it? I'm going to talk a little bit about our Resilient Materials for Life, or RM4L project, that's occupied our time over the last 5 to 10 years. I'm then going to have a look at vascular networks for self-healing concrete in a little bit more detail and cover sort of experiments that we've conducted there, and then looking at modelling vascular networks, so some of the work my colleagues have done in terms of numerical modelling, and then some thoughts on the future and where we go really from that. Whilst I'm giving this talk today, I really can't proceed without making mention of the team at Cardiff that's been working in this area at least for the last 10 years, and some of the people on this slide and their work will come up throughout this presentation. And nothing I'm presenting today could have really been done without them. And essentially these 24 Cardiff-based researchers are the co-authors of this presentation. We have a number of academic staff, we have postdoctoral researchers, PhD students, and we can't forget the many undergraduate and postgraduate taught students who have contributed to this work through their dissertation. We also have colleagues at both Bath, Bradford and Cambridge University, and our external collaborators such as University of Venice, Florence, and a series of material suppliers that have worked closely with us over the last 5 to 10 years. So to start off with, I think it's important to define the problem. Why do we actually need self-healing concrete? Well, many of us here today are very familiar with concrete. Concrete is a material, concrete in terms of structural design. And we all know that concrete is weak in tension, and due to a number of reasons, it may well crack during its service life. This then permits the ingress of harmful compounds such as chlorides or sulfates that can cause longer term and serious deterioration of our concrete structures. And you may say, well, we know that's what happens, and that's why we maintain our structures, but we invariably repair them from time to time. But do we really do that efficiently, is the question that we need to ask ourselves. And perhaps the answer to that question would be no, because repair and maintenance of structures isn't without problems. Indeed, the current figures that we look at in terms of repair and maintenance of mainly concrete infrastructure in the UK is approaching £50 billion per year. And this has significant interruptions in terms of traffic congestion and rail closures for our general public. And the economic impact of this is actually difficult to report. We also have the impact on global emissions, and in particular carbon dioxide emissions from the cement production, not only the cement that we use in our repair and maintenance techniques, but perhaps in replacement of our ageing infrastructure as it comes to the end of its service life. Indeed, when we design our current structures, we design them to have a specific service life. We understand that the material is going to degrade and that will have to enter into a number of repair cycles throughout their lifetime. But these repairs often seem ineffective. Indeed, in the EU, there are figures that in 5 years, 20% of repairs will fail, 55% in 10 years, and most of them in 25 years. And this normally happens because repair invariably happens too late. That is, when repair and maintenance is identified as being required, there often aren't the funds there to support it. And when they do become available, the deterioration has progressed such that the repair may no longer be suitable. So what if we were to have structures that could actually look after themselves, that could actually self-repair, self-diagnose damage and self-heal when damage occurs? This would then help move away from the need to go in and continually repair and maintain our infrastructure and make our structures a lot more, and materials a lot more autonomous. So in the UK, the work to develop autonomic self-healing concrete has been led by 2 large UKRI EPSRC, that's the Engineering and Physical Sciences Research Council, funded projects: Materials for Life, which was 2013 to 2016, and then Resilient Materials for Life, our RM4L project, which ran from 2017 and finished in October 2022, so literally a month ago. This is a partnership between the universities of Cardiff, Bath, Bradford and Cambridge. And it is through this, or the work that's conducted through this collaboration, that I'm going to be reporting on today, with specific focus on the work at the Cardiff University and our work on vascular networks on self-healing concrete in particular. Although we have no current funding, the collaboration is still very much alive, and we're pursuing ways in which we continue to work together to deliver our bold vision and mission, which I will come back to shortly, and to be able to develop these technologies to the point at which they can be accepted on site by practicing engineers. In Resilient Materials for Life, which was a £5 million programme grant, we had, towards the end of the project, 18 investigators that are academic members of staff, 15 research staff, and more than 20 associated PhD students across the 4 universities. We've been supported, and gratefully so, by our external partners and our 2 external boards, the first being the ESB, the External Scientific Board, where we've been supported by researchers in self-healing concrete and self-healing materials more generally throughout the UK, the Netherlands, Belgium, and China, and the Industrial Advisory Board, who have regularly fed back on our scientific progress and ensured practical relevance of the technologies we're developing. It is the Industrial Advisory Board that represents those that will ultimately be responsible for implementing self-healing concrete in practice, and they come from throughout the supply chain, and they involve material scientists, concrete producers, civil engineers, civil engineering contractors, consultants, and at the end of the day, the clients who will be specifying and requesting these materials. I mentioned we have quite a bold vision and mission, and it really is to reflect that, as you know, our structures are still susceptible to damage, and therefore the need to develop these resilient materials and structures whilst being prudent with our natural resources has never been more pressing. Indeed, since drafting our Resilient Materials for Life project in 2016, the landscape surrounding climate change has changed significantly. As a research consortium, we had, and we still have, an ambition that by 2050, we can create a sustainable and resilient infrastructure and built environment comprising materials and smart structures that are able to continually monitor, regulate, adapt, and repair themselves without the need for external intervention. RM4L and its inception was a key enabler of this transit ambition, with its own vision of achieving, by the end of the project by 2022, a transformation in construction materials using a biomimetic approach that will create materials that can adapt to their environment, develop immunity to harmful actions, self-diagnose the onset of deterioration, and self-heal when damaged. This innovative research into smart materials will engender a step change in the value placed on infrastructure materials and provide a much higher level of confidence and reliability in the performance of our infrastructure systems in the future. So moving on to looking at some terms that are going to be relevant for the talk today, we have a series of terms as agreed by a RILEM technical committee, such as self-sealing and closing, which is the ability of closing cracks. And I think it's important to understand each of these when I go on to talk about self-healing and self-closing and self-sealing. We have self-healing, which is the ability of closing cracks and restoring physical and mechanical properties of the material. We have autogenous healing, so self-sealing or healing due to the own concrete's constituents. Now, it should be no surprise to any of us that concrete has the ability to heal autogenically, whether that be through continued hydration, deposition of materials, carbonation reactions that are happening throughout the matrix. We have swelling of the cement matrix. And this isn't anything new, but there are ways in which we can enhance these by ensuring at the end of the day that we limit the crack widths to allow this to happen. We also then have autonomic or engineered healing, so self-sealing or healing triggered by engineering additions. And this leads me to the chart we have below, which really looks at these new composite materials. So on the left-hand side, we have our intelligent materials, which are materials such as skin and bone that are able to have the ability to not only sense, but also to react to stimuli and do so in a regulated manner. This is where man-made materials are very much at the conceptual stage. At the other end, we have sensory structures, which lack actuating ability, but have sensory ability. For example, smart bricks that can sense temperature change and vibrations in buildings. We then have smart materials, where smart materials, on the other hand, are engineered materials which are able to provide a unique beneficial response when a particular change occurs in its surrounding environment, such as piezoelectric materials, smart gels which can swell to 1,000 times their original volume, and shape memory polymers which have the ability to return to their original shape after being stretched or elongated due to an external stimuli such as heat. We then have smart structures, which are engineered composites of conventional materials which exhibit sensing and actuation properties due to the properties of the individual components. And this is where we sit with our self-healing concrete. We can have modes which are either autogenous healing or autonomic healing. We can have passive and active modes of activation, whether that be requiring intervention or human intervention in terms of an active mode, or a passive mode, which will happen as a function of an external or a stimuli within the material itself, which will then trigger healing. So in terms of autonomic engineered healing in cementitious materials, this is the main range of technologies that we have. For intrinsic healing, we have fibers, superabsorbent polymers, or perhaps mineral depositions. We have capsule and vascular systems, and it's where we sit in terms of Cardiff University under the vascular system, whereby we perhaps rely on minerals or bacteria or perhaps polymers to help us with that healing process. We also have shape memory polymers, as I mentioned on the slide previously. So these are materials which have been stretched beyond their original state, and on heating can return to their original form. And in doing so, for us and how we use them in the material, they actually provide a crack closure technique. We've also been involved in the development of some shape memory polymer fibers and different polymer reinforcement units, which also help to restrict crack width. And if we can restrict crack width, we can also encourage autogenic healing to happen. So I won't be discussing the development of our shape memory polymers or our fibers today, but we have progressed these technologies to a point where larger scale trials are now possible and are in progress. So before speaking about vascular networks, it is probably worthwhile me mentioning that something about healing agents and healing cargoes. Now, the challenge of compatibility, that is healing systems which are compatible with their host matrix, is something that we have to address, and we have done that through our selection of cargoes. As you can imagine, the range of cargoes tested has been extensive. There are those with strong healing abilities, such as epoxy resins and cyanoacrylates, to those which combat chemical deterioration, such as green corrosion inhibitors trialed by our colleagues at University of Cambridge. We have tried and tested a number of cargoes to determine their ability to be encapsulated for long periods, their ability to flow, to react and yield good bonding within the required timescales. And it's all of these together that really set the criteria for the selection of what it may be a good healing agent for a self-healing concrete structure. We've also looked at a range of other healing agents that we have been tailoring for our self-healing concrete. The first being adapting cyanoacrylates such that they aren't as reactive as they would initially be, that they can survive a little bit longer during the encapsulation process and won't react with the same vigor that they would ordinarily. And we've been doing this with our colleagues at Venice University by adding and amending the formulation of the different cyanoacrylates. We've also looked at anaerobic glues, so glues which will react without the presence of air, and that is often the case when we're deep within a crack. We've also looked at different lithium silicate formulations and tailoring the amount of lithium that we have to encourage or to enhance the healing response that we see. There are also some bicomponents, two-component healing agents. So in the case of our polyurethanes, we've used amine functionalized silicon nanoparticles as a catalyst for the pre-polymer. So this encourages the healing reaction by virtue of accelerating the foaming potential of a polyurethane. And then we very recently have been trialing bacterial spores and nutrient sources within our vascular networks in collaboration with the work at University of Bath. So in terms of the vascular network inspiration, where does it come from? Well, we have drawn our inspiration from biological vascular systems. Now, these systems are complex, intricate, they're three-dimensional, they're hierarchical, and they're multifunctional. The healing agents that flow within them are under pressure and can be replenished and are highly compatible with the host matrix. So where on earth do we start in terms of our concrete structures and our vascular networks? Well, we started with basic one-dimensional and then two-dimensional linear structures. Our colleagues at the University of Cambridge then looked at branch structures, and then we ourselves have then continued to look at alternative network forms to be able to host healing agents, to be able to host a range of healing agents, to be able to crack at desired strain levels of strain, crack widths, and to be able to deliver healing agents to where we need them to be. So how have we been placing these in our structure? Well, we've been having to embed these in a manner of forms. Now, vascular flow networks are attempting to stimulate the way flora and fauna heal themselves by having this inbuilt network to supply healing agents. It overcomes the lack of healing agents that may occur during the lifetime of a structure, for example, in conventional microcapsule-based products. We're able to provide a wide range of healing agents that we can pump through the flow network, perhaps from a series of reservoirs that we see on the left-hand side of this, on the right-hand side, sorry, of the screen here, which allows us to not only put things through the network, but also empty the network such that we can perhaps supply different healing agents at different times throughout the lifetime of a structure to be able to target different levels of damage and different types of damage. How have we created these? Well, we've created hollow channels within our concrete specimens by first using glass tubes, which proved pretty reasonably impractical in terms of how to place them, how to seal them, how to get them to crack at the right location. And we finally opted for techniques in which we had polymer tubes that we could withdraw after curing of the concrete, which would leave in place these hollow channels. And we used a series of these 3D printed connectors that we see here in the middle and the right-hand side, which would ensure continuity of the channels at the places where the channels crossed each other. A lot of our base work was done using cyanoacrylate and sodium silicate, and this was really such that we could ensure that we could get very rapid results in the case of cyanoacrylate, and also from our sodium silicate that we chose a healing agent that was actually chemically compatible with a cementitious matrix. We've done a lot of our tests in terms of our vascular networks with beams, looking at 3-point bend tests, usually in displacement control, a standard size beam, generally with four channels of 15 millimeter center to center, 4 millimeter diameter with some 6 millimeter supply tubes that came out of the channels at either end. And this allows us to either leave it open to atmospheric pressure or to actually apply pressure to help drive the healing agent into the crack zone. We tend to notch our specimens such that we have good control over the placement of the network and when the crack's going to form. And then we have our evaluation of healing. So this is really setting the scene for how we're going to report our healing. So we have two healing efficiencies that we report: our index of flexural strength recovery and our index of flexural stiffness recovery. So we have our typical load CMOD loading cycle, at which point we have our peak load. We then carry on loading until we get to our desired crack width. We then unload, and then after a period of healing, depending on the healing agent, it could be days in the case of cyanoacrylate, it could be hours, or it could be weeks in terms of sodium silicates. We then reload until we get to a peak load and a new crack formation, at which point we continue loading again, either to a predetermined crack width or until failure. And as saying, using the parameters that we see in the graph here, we can report not only flexural strength recovery, so that's recovery of the damage portion of the original loading cycle, or we have flexural stiffness recoveries as well that we can report. So we have also considered sodium silicate in the vascular network. So we had 4 channels in beams, sodium silicate under 0.3 bar pressure, and we wanted to look at the influence of damage age and healing time on the healing response. We can see that the results really aren't that dissimilar, and it does demonstrate that despite the age of first damage, that the healing times for, or any providing healing times for sodium silicate in excess of 7 days is not necessarily, and this is probably due to the exhaustion of available calcium hydroxide on the surface of the crack. What we do see though are very similar flexural strength recovery, so that's 27% for the first set and 22% for the second set. And this really confirms what we see generally for our sodium silicate specimens, in that we tend to reach a ceiling value of about 30% for our flexural strength recovery. For our vascular network beams, when we look at different healing agents, we have sodium silicate, we have lithium silicate, and our super stabilized cyanoacrylate. So that's really a super glue that we've tweaked ever so slightly to make it more stable in its point of encapsulation and not quite as reactive. We saw that we could achieve repeated cycles of healing over 2 to 3 cycles. And what we have with our cyanoacrylate is an increased peak strength in each one, which is very encouraging in terms of demonstrating that we could completely recover any damage that we saw in the first and second load cycles. But in actual fact, what we did notice was that we had some blockage in some of the channels for our super stabilized cyanoacrylate. We did get positive results for all our healing agents. And what we wanted to do, because we were cracking these to 0.3 millimeters each time and opening up again to 0.3, we really wanted to make sure that we could achieve similar sorts of healing at the smaller scale, so crack widths down at 0.15 millimeters. We also then wanted to look at the range of environmental conditions on healing agent longevity. So it's not only the fact that our structures have to survive freezing and thawing cycles, wetting and drying cycles, but also we will expect our vascular networks and whatever they're containing, whatever they're encapsulating, to be able to do the same without any serious deterioration and compromise of the results. Taking that work on further, then we looked at cyanoacrylate, and we looked at a series of tests in which we could actually hold the crack open for certain durations of time at a crack mouth opening displacement of 0.15 millimeters. And what this really was aiming to do is to demonstrate whether we could eventually get to simultaneous damage and healing with our cyanoacrylates. And the work has also confirmed the benefits of pressurizing the healing agent and determine the optimum pressure range for a certain type of healing agent. So we held these cracks open for set periods of time, allowing the cyanoacrylate to cure before proceeding with the loading. The results showed a modest increase of healing index from 2 to 5 minutes, although the results suggested that healing was substantially complete, about 90% of it within the first 2 minutes. A clear trend in all of the test results is that the post-healed softening branch of the load CMOD curves, so this is second stage here, and here, and here, we had graphs which are steeper than the corresponding pre-healed response, which is consistent with the fracture energy of the healed material being lower than that for the virgin material. The tensile strength of the cured CA is approximately 21 megapascals, which is considerably stronger than the tensile strength of the concrete. And this implies that a specimen will not re-crack directly through the cured agent, healing agent, but rather re-crack directly or adjacent to the healed zone, and so a crack will form around it. However, as pointed out by previous researchers, this interface zone isn't formed of only plain concrete, since the cyanoacrylate actually permeates into the microcrack zone adjacent to the macrocrack and creates a cementitious polymer composite with a high compressive strength. Here we have slightly different tests to the ones I've just seen on the previous slide, in that we have varying CMOD rates to achieve simultaneous damage and healing in our specimens. So the results differ from those in that the post-heal peak loads are significantly lower than those of the fixed static crack tests. The post-healed responses exhibit lower average rates of softening, and the post-healed responses exhibit multiple peaks for nearly all specimens tested. It is believed that these self-healing responses indicate that multiple healing damage events occurred and that damage and healing progressed simultaneously. So as a bit of crack was healed, it would reach a higher strength, it would then crack again. The graphs on the slide show considerable variability both within the test sets and between sets, and it's noticeable that the responses become smoother as the CMOD rate increases. The latter trend is attributed to the fact that as the CMOD rate increases, so does the rate at which the healed material is also re-stressed. And therefore, each component or the elemental area of healed material reaches the re-damage threshold more quickly and in any one location. The relative area of healed material that has reached this threshold is less, and the results in smaller jumps in the response due to rehealing and damage. We have then extended our work to vascular networks in slabs, so looking at orthogonal and diagonally placed reinforcement and vascular networks loaded with sodium silicate and tested these simply supported slabs under a centrally applied point load. And what we can see is that we had good flow of healing agent out of our vascular networks, and we managed to get some reasonable stiffness recovery of about 75%. This gave us confidence to go one step further and to look at including our vascular networks in a series of wall panels. Now, these were created in conjunction with our colleagues at universities of Cambridge and Bath, who tested their other technologies in some of the other wall panels. Altogether, 5 wall panels were made. Several walls had vascular networks placed within them, but only one was actually loaded with healing agent. The walls themselves were 1 meter wide, 1.8 meters tall, and 150 millimeters thick. The placement of the vascular networks can be seen on the slide at the moment, whereby we use these pink 3D printed connectors to make sure that we had good continuity at the points where the channels crossed each other. They were then extended to the side where a series of packers were used to be able to place the healing agent within the system. We used a series of displacement monitoring techniques. We actually loaded the walls through a pre-stressing bar on the back and essentially created a tension crack across the front of the specimens here. We looked at the external face and used a series of LVDTs, digital image correlation, which is why you see these speckled patterns, and optical microscopy to look at the propagation of those cracks. We unloaded and repeatedly loaded those walls over a period of 6 months and then had a look at the final results. And this is just an image to show the panels in situ. Panel B, which is this panel over here on the left-hand side, had the vascular networks with sodium silicate in them and also had a series of shape memory polymer tendons in them in accompaniment. There were vascular networks in a series of other panels, these control panels, but they were left empty and just used as our control case. So what was the outcome of the trial? Well, it was an interesting outcome. I wouldn't say that it was particularly successful because when there's a lot of reinforcement in an element, it's actually very difficult to separate the pre and post damage loading response and being able to attribute anything to the actual self-healing response and action. In our case of the sodium silicate was quite difficult. Nevertheless, we had proof of concept, feasibility and scale up and the first UK site trial. We realised that we needed additional time for fixing and fulfilling. There were some concerns about the cover zone vulnerability, especially with these channels quite close to the surface. And we realised that we needed pressure in closed systems to overcome the negative pressure in the event of only one channel breaking rather than multiple channels. What were our conclusions? Well, this was probably best limited to precast operations and led us to really think about alternative forms of networks that we could use to address some of these challenges. So welcome to the mini vascular network, the MVN or TET, as sometimes you'll hear me refer to them. These are single channel 3D polymer lactic acid printed units with hollow ligaments, which are able to store healing agent in a dormant state. They are 3D printed, as I mentioned, and they are filled with the healing agent and sealed with a silicone plug. They provide a practical and convenient method to supply healing agent to serviceability size cracks, so from 0.1 to 0.4 millimeters, although they break particularly well at 0.3, and that's been the focus of our design. We have the fracture surfaces of the ligaments. When a crack intercepts two of the ligaments, they are obviously the healing agent being exposed to the atmosphere, and that provides sufficient attractive or capillary driving force to take the liquid out of the minivascular network. These units are highly customizable, reproducible, and hopefully easy to industrialize, although that is one of our current challenges. These units themselves are about 40 millimeters ligament length, and they have an internal diameter of 5 millimeters and a wall thickness of 0.5 millimeters. So we've tried these mini vascular networks in a similar form to our vascular networks in terms of testing. So we've done 3-point bend tests. We've used combinations of 2 and 3 TETs, mini vascular networks filled with sodium silicate, and we saw clear evidence of ligament breakage, and the crack plane coverage of sodium silicate in the cross section approached 100% in all of the specimens tested, as can be seen at the bottom of the slide. It is worth highlighting that a small amount of sodium silicate was found within the units after breaking, and the specimens containing 3 TETs, while the sodium silicate was almost all solid or dried in specimens containing 2 TETs. We also have instances of repeated healing with these cycles of 2 and 3 minivascular networks. At first sight, an increasing number of minivascular networks does not appear to have a positive effect on the flexural strength after healing. This suggests that not all minivascular networks were intersected by the crack, and thus not all of the sodium silicate stored inside was able to be released during the healing process. Nevertheless, when considering the fracture energy, the recovery index underlines a positive influence of a greater number of minivascular networks. After the third damaged healing cycle, the concrete minivascular network system appears to have consumed the reservoir of healing agent within the TETs themselves, within these minivascular networks. The strength recovery index towards the end is negligible. Nonetheless, a recovery stiffness is still notable of 5% for our 2 minivascular network system and 9% for our 3 minivascular network system. In order to widen the applicability of these minivascular networks to a wider range of healing agents, we decided to undergo a bit of a design challenge to create dual channel minivascular networks. So they are concentric channels. It's almost like a minivascular network within a minivascular network. And what we needed to do to achieve this was actually tweak the printing process slightly. We needed to make the ligaments a little bit thicker. We needed to make the wall thickness a bit thicker. We needed to provide internal supports to support the internal channels, and therefore these larger units tend to rupture at crack widths of 0.3 to 0.35 millimeters. The outer wall dimensions are 0.5 millimeter. The inner are a little bit thicker at 0.75 millimeters, and that's really to make sure that that inner channel is impermeable, to really make sure we are securely encapsulating that inner component. The problem with obviously bicomponents, so two component mixes, that once they are in contact with each other, you get them reacting, and therefore we needed to make sure we satisfactorily separated them during the period of encapsulation. With we looked at different healing agents, so sodium silicate and what we would call promoters of healing, and epoxy resins as well. So our epoxy resin was a two-part epoxy resin in solution. Both components had quite low viscosity but high hydrophobicity. And then our sodium silicate and our promoters of healing were our sodium silicate solution and nanosilica dispersion, and our sodium silicate solution with a nanolime dispersion. And both of these, or especially the nanolime, was in an alcohol suspension. We looked at combinations of two single minivascular networks with either sodium silica and a promoter of healing in the alternative one, or a dual minivascular network, a dual channel one with an inner channel with the nanolime or nanosilica and the external channel with a sodium silicate solution. And again, placed at the bottom of a mold, concrete poured around them, and then undergoing 3-point bend tests. In terms of the response, it's important to ensure that whatever we're placing within the concrete structure does not have too much of an influence on the mechanical properties of the host material. And if we look at the inclusions of these dual channel networks, we can see that even when they are empty, they reduce the flexural strength by only about 10% at 7 days. However, when we got to 28 days, which I haven't shown on the slide, they had negligible impact on the flexural strength. The dual channel TET actually had a reinforcing effect as observed in this post-peak response. So there's a bit of reinforcement action being offered here. With the dual channel minivascular networks, we had evidence of reasonable healing. So our flexural strength recovery for sodium silicate-based systems is about 30%, as I mentioned previously. So we're not really too far off there. Especially in systems such as the vascular network systems, which we can provide quite a bit of pressure to ensure it flows. So actually achieving about 20% with these minivascular networks is actually good going. We see very little difference between the two minivascular networks with sodium silicate and a dual channel minivascular network with sodium silicate. So there's very little difference between those results. What we can see that with a simultaneous presence of nanolime and sodium silica at the time of damage, this has promoted the formation of calcium silicate hydrate and thus resulting in an enhanced healing performance. And that is about 27% that we can see on the screen here. We didn't see the same sort of effect with the dual channel TETs filled with sodium silica and nanosilica. And again, we're approaching what we would expect to be our ceiling value for minivascular networks with a sodium silicate solution inside. With most of these healing systems, especially when we're using sodium silicate, we actually tend to get better stiffness recovery than we have from our strength recovery. So we generally tend to get sort of upwards of sort of 45–50% when we consider our stiffness recoveries. And that's been confirmed by, again, what we can see on the screen now. And again, there was good evidence of release of the healing agent on the crack surface. So anywhere between 50% of the crack surface was covered with the healing agent, up to about 66% in the case of the sodium silicate with nanolime that we see in the middle here. So evidence of not only healing, but also stiffness recovery and flow on the crack face. We then wanted to move on to different versions of our minivascular network. So what did we do next? Well, we wanted to provide a system that we could perhaps place within a mortar joint or very close to the external surface within the cover zone. And we wanted to be able to deliver perhaps sealing agents or anti-corrosion agents to basically reinforce the cover zone in these materials. By moving towards a slightly different form of mini vascular network, we could also make them suitable for other materials, and as such, the sort of healing agents that you use, that overcomes some of the problems with encapsulation, with respect to, the compatibility and the longevity of those healing agents within these mini vascular networks. So these ones are actually minis, they're mini versions of the mini vascular network. And what we did is we just tried a few trials to begin with, looking at placing these in beams, so actually creating sort of combinations of these. So we actually double them up together. We place them on different printed spaces, whether they're 5mm or 7mm spaces, and we filled them with just general ink or a sealing solution, just to see, if we can get things actually released out of these. So they release agent between, say, 0.04 to 0.1mm cracks, so they're working within the range that we want them to work. We need to break about 4 ligaments for each double combination to get flow coming out. And then we can, say, place these in molds and test them in exactly the same way we've tested our prior vascular networks. And what we saw, again, ensuring that we don't have any negative impact on the performance of our host material by including them within the material itself. We saw that the beams with these mini networks in have marginally lower peak strength compared to the control, although nothing really to worry about. We had better response out of those which are placed at 7mm away from the surface rather than 5mm. And also we had good coverage on the crack planes. You can see bottom right on the screen, we have evidence and clear evidence of this ink flowing out of these mini vascular networks. It's important that, and I think we're quite unique in the fact that our composition of our team in Cardiff actually has experimentalists working alongside material scientists that sit alongside numerical modelers and civil engineers and designers. And so this work I'm just going to talk briefly about here is actually being conducted by colleagues, but it's important to recognise that it really does give us all the necessary tools for being able to further develop, refine and optimise our healing systems. We've been involved, obviously, in the experimental side of the work, providing data to our numerical colleagues on how and what the mechanical damage looks like, the nature of the healing agent, how it is transported, and then examining the sort of the healing agent curing and healing process. And in tandem, our colleagues have been developing the model framework, so looking at different model theories in terms of 2D and 3D finite element code, and extensively validating this code against the experimental data they've been given. And what they also want to do now is widen the applicability of the code to be able to look at perhaps autogenic systems or perhaps other healing technologies, and then apply the model to the design of material systems. So we're then working towards sort of design codes. So we have our model system, and again, this has just been based on, we started with the vascular network system, 4 channels filled with the healing agent, in this case cyanoacrylate. And what they could do is model this system and then look at the different components that needed to feed into the model to be able to represent what we see in the lab. So first of all, there was a series of experimental evidence they needed. They needed to look at how, with respect to the healing agent in particular, how its contact angle changed with velocity as it flowed into the crack, and then the change of viscosity with curing. So as soon as a healing agent hits a cementitious matrix, actually what you see is a reduction in viscosity as it starts to cure immediately. We then looked at sorption, so how it would flow through a crack face. We looked at the curing front of these, so at a distance away from a concrete surface, how does that curing front develop over time to be able to give that solid material in the crack. And then we looked at capillary rise tests in discrete crack using different crack configurations and crack mouth opening displacements to look at those kinetics of that capillary rise. And then our colleagues were able to use all of this information together with their special finite elements and cohesive zone models that I've been working on, look at modeling the cracking. So here we have a cube which is just being pulled apart under tension. We're supplying healing agent to the crack zone, and we're able to model that cracking stage and the flow of healing agent into that crack. We're then able to look at our beam system and set up in terms of 4 channels of network flowing in. So we get flow from our vascular network into the crack plane, as such that we can see, coverage of cyanoacrylate on the crack plane. We are able to extend this to some of the networks perhaps our colleagues at University of Cambridge have been looking at in terms of these branch systems. So again, having flow from our network into the crack plane and covering the crack plane. And then also using similar models or part of the model to look at how we get flow using things like Rich's equation for fluid flow and porous media, how we get flow away from that crack zone into the matrix, into that the material either side of that crack. And then lastly, we have this healing agent curing. So looking at how that depends on the crack opening and the rate of which that crack opens, and look at how that curing front progresses and the viscosity change with curing. And that allows us to understand how that material builds up in the crack, how it cures, how it heals, and therefore how that healing component can be then reflected in the finite element model. So if you think back to some of the tests that I showed you earlier, the test results, I talked about using different CMODs and using different static crack periods of it, which would keep the crack open for. And we tried, my colleagues tried obviously their model that was simulating this, and I think you can agree we get quite good correlation in terms of being able to understand at a certain crack width, if we hold it open, we obviously get flow of the healing material that's happening, we get regain of strength, and upon reloading again we can mimic the response that we see. And again, at different CMODs, you get the influence at the rate at which that healing agent is curing in that crack, that progression front of the curing, reflected in the response that we see here. So what's next? And I hope this plays tricks on your eyes, but there are hundreds of mini vascular networks on there, and that is one of our big challenge, is how can we manufacture, fill, seal and place millions of these units in our concrete structures? And we want to produce biomimetic networks using conventional manufacturing methods such as perhaps extrusion, injection molding or 3D printing, but we need to do this at high volume and at reasonable cost. And we need strategies to manufacture these now that will support perhaps novel manufacturing techniques, and we'll be able to use smart and sustainable materials actually not only in the manufacturing process but as part of our product as well. We want to be able to use recycled plastics. We want to be able to, at the end of the day, take our structures, if they are going to be demolished in 200-300 years time, and use the materials and be able to recycle them and reuse them again. So that's really important to us as one of our main challenges. We also want to have a look at different forms of vascular networks. So these straight channels aren't appropriate for all sorts of structures. There are different types. Perhaps there's complex joints or mortar joints that we need to continually refine the physical makeup of our mini vascular networks to be able to address those sorts of construction techniques and joints, and be able to give or provide self-healing to a far greater range of structures. There's also the potential now to look at the repair of historic and culturally important structures, so those which do really use lime-based materials, especially in repair, and being able to see how we can develop vascular networks to be able to sort of sense damage and to provide feedback on how those repairs are lasting. And a colleague of ours is actually studying this as part of the Leverhulme fellowship at Cardiff University over the next 3 years. We're obviously intrigued looking at novel prophylactic agents to actually continue our work on healing cargoes and optimizing those, and looking at networks that can self-sense damage themselves and perhaps be part of the sensing technique that we wish. We also have design standards and specifications. Now, we've had contractors and client bodies who have shown significant appetite to use self-healing concrete, self-healing materials in their structures. But actually what we need now is a way of ensuring that we can design with these systems. And this is where the numerical simulations that my colleagues are conducting will play a really important role. There's a long list of references there, but not exhaustive. There's far more work that we've been able to achieve that I haven't referenced there at the moment. And I just want to say thank you for your attention today and for giving me this opportunity to talk to you.